So I read my first problem here that tells that a heavy tapered rod of original length L is hanging from a fixed support. The radius of the cross section of the rod increases linearly from a value of R1 at the upper end to R2 at the lower end. The rod is made from a material of density rho and Young's modulus Y. Determine the elongation of the rod. So there is no figure given with the problem, and the level of the problem is tough, therefore 3 dots against it. We shall understand first that for any rod of non-negligible mass, the tensile force in hanging position varies with length of the rod as you go from the top to the bottom of the rod. So let me introduce a figure here. This is the ceiling, say, and I take initially a rod of non-negligible mass but of uniform cross section here. So this is the rod's enlarged view. I am showing little enlarged cross section here. So in hanging position, this rod is in equilibrium under 2 forces. One is the force of gravity acting vertically downwards. Other is the contact force exerted by the ceiling at the topmost point. So if the mass of the complete rod is equal to capital M, the force of gravity is mg, and suppose the contact force given by the ceiling on the rod is taken to be the vector r. Obviously, for the equilibrium of this rod, this contact force given by the ceiling r must be equal to the force of gravity on the rod. So under these 2 forces of equal magnitude opposite direction, the rod is in equilibrium. It is obvious that the tensile force acting at the upper end of the rod is also this r, that is mg. But if we choose a cross section of the rod at a point little depth below this upper end, suppose somewhere here, what will be the tensile force acting at this section? To find that, we can in imagination divide the rod into 2 parts by a horizontal plane that cuts the length of the rod normally. And once you divide this rod, in imagination of course, by this horizontal plane, there will be 2 parts, the upper part and the lower part. I draw here only the lower part and investigate the forces which keep this part in equilibrium. Well, this part now of smaller mass compared to the whole rod. So the force of gravity acting on it is equal to m dash g, where m dash is the mass of this portion, and it's understood that m dash is less than m. And at the upper end of this part, that is this section, suppose the tensile force acting upwards is this vector t. Now since the whole rod is in equilibrium in suspended position, either part of it, either the upper part or the lower part, will also be in equilibrium under the respective forces acting on each of them. So for this lower part of the rod, extending from this point to this point, it is in equilibrium under this force of gravity m dash g acting downwards and this force of tension T acting upwards. So I can write down that tensile force at this section, this one, the same thing. This T is equal to m dash g. Now compare these 2 figures. If we go to the upper end of this rod, this m dash becomes equal to m and this T becomes equal to r, that is mg. On the other hand, if I come to the lower end of the rod, in that case this length becomes 0, m dash becomes 0 and corresponding tension also becomes 0. So you see, for any suspended rod of non-negligible mass, the tensile force varies along its length, changing from a value of mg, total force of gravity on the rod at the upper end, to a value of 0 at the lower end. We shall keep this in mind and also note that this variation of T with length is independent of the fact whether this rod is of uniform cross section or a variable cross section like in a tapered rod. Once you understand that, we will be drawing one fresh figure to investigate this heavy tapered rod in hanging position. I introduce my next figure here to show this tapered rod. This is the ceiling, say, and this heavy rod is suspended from the ceiling. I'm just showing a little bit separation to be able to write a few things on my figure, but it's understood this point is in contact with this ceiling. Now, as they have said, the length of this rod is equal to L. I'm showing that in my figure. This is L. And radius of cross section, that is circular cross section, increases from R1 at the upper end to R2 at the lower end. So I might show here that for the upper end circular cross section, the diameter is equal to twice R1, and similarly for the lower end the diameter is equal to twice R2. And they have mentioned rod is made from material of density rho and Young's modulus Y. Let me write it somewhere. Density is rho, Young's modulus is Y. We have to find out elongation of the rod under its own weight. So what we do, from this upper end of this rod in contact with this ceiling, I go to a depth of, say, Y, a variable quantity. I'll be taking the downward direction as plus Y direction. So I show it also on my figure, and go to a depth of Y, a variable quantity, from the upper end, and show here a cross section, also circular, of radius, say, equal to R. So I'm using blue color here for quick distinction. Once again, from the upper end I come to a depth equal to Y, which is of course less than L, the length of this rod, and consider a cross section of radius R and diameter twice R, so that the value of R is greater than R1 but less than R2. R1 is smallest, R2 is greatest, somewhere between. The R is between R1 and R2. And note also, since they have mentioned radius increases linearly from R1 to R2 over a length of L, we get an important relationship here, that is the rate of change in radius of cross section with length, that is dr dy. I could write like that. This is coming out to be the difference in radius over the whole length, that is R2 minus R1 divided by the whole length, that is L. Once again, dr dy is the rate of change in radius of cross section of the rod with distance taken to be y in my figure, so it's dr dy, that equal to total change in radius R2 minus R1 by total length, that is L. We shall make use of this in near future. It's equation number 1 for me. Now, my approach will be to consider an infinitesimal element of this tapered rod and identify the tensile forces acting on this.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.